Okay, hello everyone. So today we are going to look at WarpSync. So this is a video that I should have done a long time ago, but I guess later is late is better than never. So we're going to do it today. Well, it's going to be obvious, but I haven't really scripted or planned this video too much in advance. I have some points I would like to go over, but other than that, it's gonna be pretty much ad hoc. So let's get started with WarpSync, what it does. So it's in a nutshell, it's a way to synchronize for Zcash and Zcash, obviously, and this is a way to synchronize the wallet with the blockchain for Lightwallet in a more optimal way than what other Lightwallets have been doing so far. So I'm gonna start with very simple stuff. So what's the data model for Zcash? And then what are the functions that a Lightwallet should have? Then we're going to talk about the difficulty that is associated with Zcash, the particularity that Zcash has, and that makes synchronization a bit much more painful than other wallets, and how we can address this. So there are basically three schools of thoughts about how to do synchronization. There's the regular SDK, the ECC SDK, there's BlazeSync, and there's WarpSync. So we're going to talk about these three near the end. And finally, then we're going to focus obviously on WarpSync. Okay, so the first part is relatively easy. So what's the data model of Zcash? Well, first of all, if you want to have information about ZWallet, YWallet, and well, now it's also called WarpWallet. The only reason why I had to call it WarpWallet is because on iOS, the iOS App Store, ZWallet is taken by a completely different project. So over there it's called WarpWallet. So, but it's other than that, it's exactly the same thing. Okay, so if you want to have more information, you can go to this website, which is basically the GitHub.io, the GitHub pages associated with the project ZWallet, and then it has all the documentation related to the project. All right, so okay, finally, what's the Zcash data model? Okay, that's fairly straightforward because is nearly directly the same as a Bitcoin data model. So you would have transactions, and transactions create new, what they call, Bitcoin call them UTXO, unspent transaction outputs. So transaction outputs is clear because it's created by a transaction, and it's unspent because once you have just created it, it's not spent yet. So transaction uses previously unspent transaction output, and they create new ones, which is essentially the same as the model where when you pay somebody, you use the coins and the notes that you have in your wallet. You give the ones that you have not spent before. Obviously, you don't want to have a system where double spending is allowed. That would completely defeat the purpose of having money. So the coins and the notes that you use have to be unspent, and you are giving to somebody, so that person will have new unspent transaction outputs. Only difference between cryptocurrency, Bitcoin, and real money is that in real world you will not be able to create new notes. You'll be basically exchanging the notes that you already have. And you would change the owner of these nodes. In Bitcoin and in Zcash, what you have instead is the ability to create new nodes with different denomination. So anything between 1 Satoshi and 21 million is a valid output. But provided that your output is the sum of your outputs, must be lower than the sum of your inputs. So you can't create money. Again, that would totally defeat the purpose of having a cryptocurrency. You cannot create more than you have provided. So Zcash is the same, except that they don't call it UTXO, they call it nodes. So among other things, the most interesting thing in the node, maybe I can find it here, is the amount, and it's the recipient, so the address where it goes through. So of course, the big difference between Bitcoin and Zcash is that the node itself is encrypted. So what I've been talking about is the non-encrypted node, so call it the plain text node. And this guy has the amount and the address and a bunch of other stuff. There's memo, there's things like that, right? But you will not see that in the blockchain. All the nodes are encrypted. So they're encrypted in a way that only the recipient of the node, or in some cases also the sender, but let's forget about that. Let's say that only the recipient of the node is able to decrypt. So decryption is encryption and decryption is kind of one way. So if I encrypt the node to send to you, so I want to pay you, you give me your address, so I'm able to encrypt a node for you. And you will be able to decrypt it, but not me. I will not be able to decrypt even the node that I have encrypted myself. Right? So if I lose the original version of the node, then it's too bad for me. I will not be able to reverse to decrypt the thing that I have sent to you because I don't have the decryption key. So this allows you to actually receive nodes for a lot of people just by providing an address. But the people who are said to be paying you, they are not able to know who else has paid you. Right? So that's a basic property of the encryption. I mean, it's something that you kind of want to have. So when all these nodes that end up in the blockchain, they all appear in encrypted form. Right? That's what we have said so far. And only the ones that you know are yours, and knowing it's yours is actually through trial and error. You have the decryption key because when you created your account address, the address would derive from a bunch of things, and among these things, it's the decryption key is going to be there. And if you have this decryption key, so we sometimes it's called the incoming viewing key, but essentially that's the decryption key. You will be able to try to decrypt the node. So you can see that it's basically the transaction has a bunch of outputs, which are so you can recognize that it's an output by the shape. Right? So this is like having a letter. So you can see that okay, this is a letter. This is not a box. This is not. This is real. Is a letter. But you would not know who's the destinator, who's the recipient. You don't know where this letter goes through and what's inside. What you can do is you try to open it, and if you're able to open it because you have the key, then you'll be able to see what's inside. If it doesn't open, then you don't see anything. And so all the nodes that happen to be on the blockchain, only a very, very, very small fraction of these are going to be yours, right? Because, well, you're not the only one, obviously, in doing transactions. So I think so far is maybe like 700,000 or maybe probably more now transactions outputs that are on the blockchain. Let's say 1 million. You don't have 1 million received nodes. You probably have something around from 30 to 100 if you have a typical wallet. So that means that for the vast majority of these nodes, they are black boxes. They are not something that you can understand, you can see. So why do you still need to care? Well, that's the first question you want to be asking yourself. And the answer to that is actually a bit complicated. So before we get there, let's see what we want to do with the Lightwallet. right? So if you take a Lightwallet, by definition, is a wallet that does not have the entire blockchain. So it's kind of by opposition to a full node. A full node will receive all the transactions, will try to maintain all the data required to verify. Well, not try, but it will store all the data required to verify transactions, and it will basically enforce that the rules of the blockchain of the protocol of the coin are enforced, right? And the Lightwallet doesn't need to do that, all that. So the Lightwallet has main task, only 3 tasks, right? So we only have to be able to receive money, to receive coins. We should be able to see the account balance, the wallet balance, and we should be able to spend money. All right, so receive, send, and check the balance. Receiving is fairly straightforward because it's basically be able to generate an address. So if you have a valid address, you are able to receive money, receive coins, and that's why you can have a paper wallet, right? So you have a program that generates an address, and that address is you write it on a piece of paper, and anybody can send money to you if they know that address. So receiving is fairly trivial, well, not trivial, but it's very easy compared to the other stuff. The 2 other things, which is like checking your balance and then sending, typically usually go together. Like for Bitcoin, when you are able to, meaning by going together, I mean they usually have the same complexity. If you are able to check your account balance, then you are able to spend, right? For Zcash, these 2 are fairly different. So I'm going to talk about one and then the other separately. So the first one, if you want to check your account balance, it's essentially knowing how what nodes you have received, right? So that's your incoming source of funds, and what nodes you have spent, and basically that's what you have paid, what you have consumed in between quotes. So in order to know what you have received, we know that you have the decryption key, and the process is going through every transaction, every output, and then trying to decrypt that output. And if it succeeds, then it's yours, right? And there's even this notion of succeed and failing is a bit tricky because, well, if it's a bunch of crap bytes, garbage, right? How do I know if I decrypt it properly? Well, there's some checksums or something that allows you to see that if decryption was successful. So this is like getting a letter and then trying to decrypt it. If you are able to read it, if it makes any sense to you afterwards, if it's then it means the decryption was correct. Because it comes like garbage, it comes. Everything doesn't make any sense. If you decrypt, it still doesn't make any sense, then that was not the node for you. So then you go to the next one and you repeat until you have exhausted the transaction. Then you go to the next transaction and then you repeat until you have exhausted the block, and then you repeat the next block, and so on and so forth, right? That's how you would synchronize, how you would find the node that you have received. So yeah, it is not it's not simple. I mean, it's not lightweight. You do have to try every node. There is no way to see beforehand which nodes are yours, besides decrypting. And the reason is because if you were able to know which nodes are yours, then other people will also be able to know that these nodes are yours, right? So there's nothing that you can do that they wouldn't be able to do, and therefore your privacy is compromised. So basically what we are saying is that we have to put the locked door in front of your nameplate, right? So otherwise people would know that this letter is addressed, this transaction is addressed to you, right? So that's step number 1. Step number 2 is knowing what of these received nodes you have spent, right? in Bitcoin, it's fairly easy because the nodes that are spent are kind of referred to by a transaction. So if the transaction takes like 3 inputs, and they will say, oh, I'm taking input from transaction XYZ, and I'm taking the 4th output from the top. So that identifies the previously received node accurately, and this allows the verifier to make sure that, okay, that node is now spent and cannot be spent again. But in a system where like Zcash, where you don't want to be able to even figure out that a node has been spent, except it was your node, of course, right? It has to be more complicated, right? You can't just say that this is that node. So this has to be also hidden. And the way they hide it is to associate with each received node a nullifier. So a nullifier is some number, some value that is uniquely calculated from each received node, and can only be calculated by the person who has has received the node. So it's not done through the encryption key, but it's something that is also derived from the seed of the account. So actually, the seed of the account produces a bunch of things. This is like it's like one of these, right? So this nullifier value, which is again associated with each received node, is something that you would have to provide at the moment you spend. But you don't actually provide it directly. You provide it through a zero knowledge proof. But we don't want to get too much into detail. But the idea is that you have to provide that something that is related to that nullifier, right? Which proves that you have it, and also it proves that you are not going to spend it twice, because the nodes that are checking the validity of the blockchain will keep track of which nullifiers have been published, have been used. So if you are trying to spend the same node twice, your only option would be to publish this nullifier twice, and it would be caught by the network. So the idea here is that the network is not able to know it's not able to match the nullifier to a particular received node, but it would at least able to know that this nullifier is related to one of the nodes, and therefore that it's a correct nullifier. And the network can also check that the nullifier hasn't been used twice. So to be used twice is simply you keep track of everything that has been used, and then you see if there's a duplicate, right? And the key point here is that proof that the nullifier that you're giving is related to a node that you have received. And we'll see that is the hardest part of the protocol in terms of doing the synchronization. So let's go back to our problem. We know now how to detect incoming funds, right? We do the trial decryption, and we know how to detect how to do the spend, right? So the idea of doing the spend is when we have received the node, we have computed the nullifier, and now to say that we are spending, we are giving that nullifier to some form. But again, all this stuff is very well hidden through because the novelty of Zcash is the Zcash dark, the zero knowledge proofs. So the idea of zero knowledge, a very, very high level, is that we are saying that we know some things. Right? We know, for example, the nullifier. We know the node position. We know the values. We know all of these things. And knowing these things is very difficult. It's not something you can guess. It's like most of these things are hashes. So if you know the hash. If you don't know the hash, you cannot guess the hash, right? And these hashes they have to fulfill some very precise conditions in order to be valid, right? Some of these conditions we're going to see, but essentially these conditions are expressing in a mathematical form the correctness of your transaction. So for example, if you're saying that transaction is valid, it should have less output than input, right? So because it's not exactly equal, because you'll be spending some of the input towards paying the fee, and that's just that will be just the difference. But saying that statement, which is basically I'm not overspending, can be expressed with an equation, right? And that equation can then be transformed into a zero knowledge statement. And the zero knowledge statement is saying that you know how to, you know, the values that would fulfill these conditions, and that your transaction fulfills these conditions, but you're not giving the actual values, so that the recipient does not know how much you have spent, where you are spending, and so on and so forth, right? But the key point is that you are not able to create these zero knowledge proof unless you had these inputs, right? So in a nutshell, that's the idea, right? Okay, so why now this is related to us? One of the inputs of this function that produces the zero knowledge proof for spending is related to your node, your ability to know which node you are spending. So it has to be one of the received nodes that you have, right? So we know that there's a million of nodes out there, and some of these are yours, and you're kind of trying to point at one of these, some of these nodes, without saying which one they are, right? So that's fairly tricky, right? And the idea of okay, so now I'm putting an illustration I found that is from the original paper on I think it's called, it was ZeroCoin at the time. So this thing on the right is on the left is what we are interested at. The thing on the right is, I think it's not exactly, it's not the same thing now. So what is this stuff here? And I have pulled this guy. I made a copy of this guy in bigger. Alright, so this stuff here, so let's forget about the stuff on the right. So I'm gonna cut this. How can I trim? Can I trim? Not trim. What about crop? What? Why, yo? Crop. Alright, so we crop this guy, and we are going to talk about this guy in more detail. Okay, let me resize this. 200%. Oh my god, it's way too big. I know. Alright. Oh yeah, now it doesn't fit anymore. Brilliant. Resize canvas. Okay. Oh my god. Sorry about that. I just want twice. Okay. 300. Okay, roughly that's 766. Alright, and then can I resize this? 200%. Alright, I think this is roughly what I wanted to do. Okay, so what is this thing? So what this thing is what you need to use This is one of the inputs to the ZKP, zero knowledge proof, required for spending. Right. So what is that? How is it built? Basically, the leaves here. So it's a tree, right? A tree is a binary tree. So you have leaves. So all the stuff that is at the bottom are leaves, and you have nodes where combining two of the leaves together, so to make this level, and then further combine 2 by 2, 2 by 2, 2 by 2 up to the top, right? And the stuff that you have at the bottom, they are called the node commitments. So the nodes that you have received are encrypted, but it's still pretty large, right? So still a bunch of bytes you have. It's pretty large because you have the memo and stuff there, right? So they hash this into a 32 byte value, and that makes the bottom of your tree. And you can see here that there are 8 such nodes. In practice, this is currently 1 million nodes. So you have 1 million of these guys. And then on the next level, you have half of that. So you have 500,000, and then 250, and so on forth, until every time is divided by 2. So then in the end, you have only one guy at the top. And then if you have a level which has an odd number of children, so for example, if we didn't have CM8, we end at CM7. It's not an issue. The rule is to use a placeholder. So we use another guy here that is predetermined, and then we still can combine CM7 with this placeholder to get that guy. And then if this level had only 3 or 5 nodes. Same thing, we will add a placeholder and then to make it even, and then we can combine 2 by 2, right? So up to the top. So one of the rules of this stuff is that the nodes are added always at the end, and the nodes are never, the leaves here, they are never removed. So this 1 million, if you have more transactions coming, there will be outputs, and then the outputs will produce more leaves that you're gonna append at the end of this tree, and you still combine them 2 by 2 until you reach the top. Right. The way of combining these nodes it's a hash, it's a Peterson hash, and well, we're not going to care too much about this, but the main thing we should know is that hash calculation is fairly expensive. Right? It takes a bunch of elliptical curve multiplication and additions, and that's something that is not easy to do, and that's not easy to do on purpose. If it was too easy to do, then the coins would be easy to crack, right? So there's a good trade-off between having something that is easy to compute, because when you start using it, it takes time. So if it's too slow, it's crappy. But if it's too simple, then it's too easy to crack, right? So this Peterson hash, we have to bear in mind that we want something that is fairly fast, but it's not going to be super fast. So we want to minimize the number of time we are calculating these hashes. And second thing is that there's no shortcut. If we need to calculate a hash, if we need to calculate, for example, this node, let me see. Yeah, if you have to calculate this node here, okay, let me see if I can have. Can I draw something here? Polar shape. I wish I could draw. No tool for drawing. Tools. Stem, move, blur, crop, pen, line, step, eraser, highlighter, I guess. Okay, does it work? Yeah, that's very not super good. Okay, so if I need to calculate this value, This then I would have to combine CM1 and CM2, and that uses the hash, right? So and I have to calculate the hash. I can't use any of the values that are pre-calculated before. This is not going to help in any way. Right, so that's one thing to remember, and also that all these are hashes. So if I need to calculate this guy, then this is going to be this value combined with this value. And why I need to do that? It's because part of the input of the ZKP function. Okay, so ZKP function is the stuff that builds the ZKP. Right, so in order to make the transaction, you are going to have to provide this 0 ZKP, and you have some very complex piece of code that is, for all manner of purposes, for us, we're not gonna optimize. It takes a few values as inputs, and then it creates the ZKP, and then you can put that ZKP into a transaction, and blam, you broadcast it, right? So all we care about here is we need to maintain enough information so that we can feed that into the ZKP function, and then we're golden, right? If we were a node, if we are a full node, then that's not too much of a problem, because all the CM1, CMX, all these 1 million stuff, we're probably going to keep it in some ways, because we have to verify that they exist. I actually don't really exactly know how the full node works, but my guess is that all these nodes are stored somewhere in the database. For a light node, Lightwallet, this is not very good. It's not something we can do, because our hardware and storage is limited. We don't have this 1 million. Well, maybe we have, but this still not going to be a good idea to store all the nodes that refer to other people's transactions if we don't have to. Right? So we have to be a bit more clever. And the idea here is that among all these leaves, only a few of them, let's say for example CM4, okay, we're going to mark CM4 as being our node, is ours. All the rest is somebody else. So the fact that they are not ours doesn't mean that I don't know CM. So because CM are node commitments, they are hashes. What I do not know is what was the original data that hashed into CM1 or CM2 or CM3. I just know the plain version of that, so of CM4. So let's say the unencrypted version of CM4, and I'm able to go from that clean, between quotes, version of CM node 4 into this CM4. But all the CM, I know them, right? And when I want to spend it, what I need to provide to that function is all the CRH along the way. Okay, so finally we're talking about that path, right? So not only I have to give CM4, I also have to give this one, because it's along the way. So I'm actually just drawing the ones that are along the way to the root. This is not exactly the ones I need to give, and we'll see why. But these are the ones that are along the way to the top, right? So you just follow the arrows on the way up until you reach the root. The trees are drawn upside down, which is always kind of weird, right? So the root of the tree is up there, and the tree is kind of growing downwards. Pretty weird, but yeah. So that path here is something that this value here we have, right? This value here is published in the block header. Right? So this last value here is something that you can verify. It's called the anchor, and it's also something that is part of the ZKP function. Right? So all these values along the way here are there to show that your node is actually belongs to that tree, right? So the fear here is that you are completely bogus, and you provide a value that has nothing to do with any of the nodes. Not only you don't know what it is, but you don't have actually any idea, right? So you provide CM, not even a CM, you provide something else, right? So we want to be able to verify that your node is part of that tree, right? And because of the construction of that tree, it's fairly easy to do so, right? So how? We know that Zcash here, right, is the result of hashing CM3 and CM4. Right? So CM3 and CM4 give this one, right? And then this guy here is the result of hashing this CRH, this one and this one, right? So we got that guy by using CM3 and then this CRH. And then to get this one, well, we have already calculated this guy. So now we can use, if I give you this guy, then you can combine these two and then you get that guy, right? And furthermore, and along the way, if you want to go up, basically every time you need to have the sibling, right? Because you already have calculated that value, the node value, but you need the other value in order to combine, right? And then you get here, and then we need this one, and then get this guy, and then I'm at the top, so I don't need anything else. Right? Sometimes you will say, oh, well, what if there's no sibling? Well, it's not a problem if I have no sibling because I'm at the edge of the tree. I would just say you need to use a placeholder, the same way that I would have used a placeholder if I had the full tree. Right? So all the green guys that I've drawn, right, are the nodes that given CM4, so all the green guys plus CM4, so I can say this guy is double colored, we can combine this and then recover the root, right? So these are the stuff that you need to maintain, right? This is the Merkle path, right? So having these values is critical for our wallet. Right. We don't care about CM1, CM2. We don't really care about any of these other stuff. We don't, because what we need to give to the ZKP function are the green guys only. And but you can say, okay, but that's not too bad. It's very easy. Let's do that. Well, the problem is that the green stuff, if you have other nodes, so if you have, for example, let's use blue. If you have this one, right? Well, if you have this one, then I would need to have CM8, and then I would need this guy here. Okay, so I need this one. CM7 is our node, and then maybe I can use this guy like that. No, that doesn't work. Let's use orange. Okay, so then we need this one, and I need this one, and then I need this one. Okay, so you get the idea, right? So you need this one. Okay, so you need this one, and then so on and so forth. So if you don't have the entire stuff, keeping track of the ones that you need is where this is a bit tricky. Right? So, and the second thing that is tricky is the fact that as the tree grows, as more nodes are added, the shape of the values of the nodes, they will change. Right? So not all values will change, and that's also something that you can optimize a lot, use for optimization, and we will use for optimization. If, for example, we already have CM1 and CM2, and they were combined to CR, this green box, then because the tree always grows and never gets updated, we know for a fact that CM1 and CM2 will never change. These two leaves will never change. Therefore, the value of this green box will never change. Right? So some of the boxes will never change. The ones that change actually are, they must have some placeholder. Right, so you can see, for example, that all this stuff will never change. This part will never change because we have it filled from CM1 to CM8. But CM9, but this one here, uses a placeholder, assuming we don't have CM9 yet, right? So this one here uses a placeholder, and therefore when CM9, the real CM9 comes, the value would change, and this CH would change, right? So some of the values change, and for a fact, we know that the root always changes every time there's a new node added. But the ones are, we can say that the portion of the tree that is fully filled, like this one here, this section here, which is fully filled because there's no placeholder, right? We have already put every possible leaf we can. Then that section will never change, right? So that's the idea of the synchronization. Synchronization is the idea that you will receive a bunch of these nodes, and then you build this data structure, but with plenty of holes. You don't want to store CM1, CM2. You don't want to store all these guys that are not yours, but you want to store enough of these middle guys right here in order to update the tree when more things are coming, and in order to provide the Merkle path, the green path, whenever you want to span that node. And that's the main challenge, right? Now we can talk about the ways the wallets do it. So we have the ECC SDK, the reference wallet, which is basically the code that is used by Nighthawk, Unstoppable, Edge, and the reference wallet. There's the code that's used by ZWallet. It's called BlazeSync, and there's the code used by ZWallet, which is called WarpSync. So the three of these guys, they have exactly the same purpose, which is maintaining that tree. And I'm only focusing on that tree because everything else is dwarfs the complexity of this stuff. Basically, maintaining this stuff takes like 99.9% of the time of the reference wallet, right? The decryption, you may think, okay, you may think that this is time consuming, but it's really small compared to maintaining the code that maintains this data structure. Is much more time consuming than actually the decryption of the nodes, the trial decryption of the nodes. All right, so let's see how it's done in the reference wallet, right? So again, that's Lightwallet, Unstoppable. So the idea, right, is that you will leverage the fact that this is append only. You only append stuff at the end. Unfortunately, I would have to simplify a bit because the details is I think beyond the scope of this overview. So the idea is that you're gonna have you're gonna maintain the nodes that make the rightmost edge of the tree at this point. So if you have CM8, it would be let me see if I could use colors. Let's use blue. It would be CM8. It would be this one. It would be this one. It would be this one, right? Actually, in our tree, it will end at this level because you don't really need more than that. Yeah, I think that's the case. Yeah, I think that's pretty much the case. If you have CM9, then this tree is completely full. So we have to add one more level. So then this becomes CM9 here, and then there's some nodes, and then we're gonna have this guy, right? So the goodness, the great thing about the incremental tree, the fact that the tree never gets updated in the middle, but always at the end, is that having this edge, this last value in a sense, is sufficient for maintaining for adding more elements. And this is kind of like so I think the easiest analogy I have for this is if these nodes had values instead of simple one value instead of having hashes. So let's try that. Let's try with values. So let's say that CM1 is 1, so we put 1 here, Why could I type? What is this guy? Oh, I have to do it this way, sorry. Okay, so let's say this one is 1. Oh yeah, I can see. So this one is 2. This one is 3. Okay, so on and so forth, right? And then instead of combining the values together, what? Can I move this guy? Oh yeah. So instead of using hashes to combine the stuff together, I'm just gonna say that to combine two values, you sum the stuff below. So 1 and 2 is combined to 3. So we put a 3 here. I need a better color than that, so I put it in red. Okay, that's pretty good. 3 and 4 are combined to. Maybe I should not have to change the color. Okay, so this is 3, right? Then 3 and 4 combined to 7. What? Okay. So far so good. Do I even care? It's not a 9. Oh yeah. Okay. Yeah. 3 and 7 are combined into a 10. Okay, and then you get the idea, right? What else? Okay, so and we say that we have CM5, but we don't have yet CM6, CM7, and CM8, right? So we have CM5. This is a 5 here. So this node has a 5. Oh my. Okay. Yes. No. Okay. More or less. So 6 is not there. So we'll say that when something is not there, the value is 0, right? So 5 is not there. 5 is there. Here we don't have anything, so it's going to be 0, implied to be a placeholder of 0. When we combine 5 and 0, we have 5. So this is going to be 5 here. This is 5. And then we combine 10 and 5. And that should be 15. 15. All right, 15. All right, so that's all the values we have, and we don't have this part of the tree at all. All right, so maybe I can delete these guys. I don't want. Where's the tools? Favorite. I don't know. Maybe just click. Oh yeah, just click. Alright, so we don't need that guy, so I'm gonna delete this stuff. Right. And okay, so this is our tree. I'll put the 5 here too. And then put a 4 here. Alright, so this is 1, 2, 3, 4, 5. Then 1 and 2 combine to 3, 3 and 4 combine to 7, 5 and 0 combine to 5. There's a 5 here, and then to 15 here. Okay, all right. So the way is one way to do it is that when we have a 6 coming, so we put the 6, all right? So we have this. Wow, this is very big. Why is it so big? What is that? Six. Why is it so big? $24. This is 24. Oh, okay. These are sizes actually. Is it? Yeah. Alright, so let's make this guy a little bit bigger. Alright, okay, let's make it really big. So this is 6. Of course, now I want it big. It's not big anymore. Okay, so this is 6. Come on. Okay, click on this guy. And I put it here. I put a 6 here. Size. Alright, so our gigantic 6 is here, right? So the 6 comes, right? And what we do is we update everything that is along the way, right? And you can see that if we have this last value, that's enough, right? So 5 and 6 combined together, and then it gives. We have to update that to 11, right? And then the guy on the right, we know that it's still 0, so we update the parent with combining with 0, so this update to 11. Right, and then this guy we had, because we have also the guy on the left, right? And then we combine that into 21. Actually, we don't need to combine the top because the top is the root of the tree. So we know that this has to match whatever is published out there. Right? So 21 is not to be kept, but that's small detail. So you can see that updating is fairly. We don't need it to have the interior nodes because the values of the interior nodes, right? All the values here, they were already captured by the 10 that's here, right? We're never gonna need it to merge this left side here with the right side here, right? We are going to need to merge this node here with this node here, but for that we don't need to have the children. We just need to have this value, this node value. So that reduces greatly the amount of data that we have to store. We don't have to store all the values here, which is 2 power n, if you add is the number of levels. But we just need to have n, which is the number of levels. Right? So that's what the reference what it does. Right? Every time we add a node, this 6 here will be combined. We update everything on the path. And then when 7 comes, and then they do the same, and every time it updates this frontier. Okay, the trickiness though is that the frontier is not really what you need to have, right? We remember that what we need to update is the green part, right? This 3, 3, and 11. But we can see that for every one of the nodes we have, the 4, and then maybe we have some other ones, updating the path is pretty much of the same order of difficulty or complexity than updating the frontier. Right? So when you have the 6 here, we would know that okay, this 7 doesn't need to be updated because the 3 is practically carved in stone by now. But because the node 5 became 11, then our new value is 11, right? That's what the ECC, the standard wallet does. It has one function. The API is fairly simple. There's only one function in the API that is important, which is append a node. So we append a node to the we use one thing that captures these green nodes, right? So for our node 4, we would need to store 3, 3, and 11 somehow, right? Or 3, 3, 5. Sorry, with 3, 3, 5, and then when 6 comes, we know that we have to change that to 3, 3, 11, right? And then when 7 comes, then this 11 will change, right? And then we go and update it. Then 8 comes, 11 changes again, and so on and so forth. So every node that you have, you are going to call the append function, right? And even though this is fairly simple, right, in terms of logically it's simple, the number of calculations you have to do is not simple, because every node that you treat it in this way is treated independently. For example, if we have if we had both CM4 and CM3, we don't use the fact that CM3 and CM4 share many nodes in common. It shares this node here. So whenever we have a node that is added, we will update the value that is kept that CM4 keeps track of. This 5 became 11, and we're going to do the same for the node 3. Node 3 would also have, basically, each node has its own tree, right? And each node, each received node will recalculate part of that tree whenever there's a new node that is coming. And remember, there's millions of them coming. So every time you have a node coming, we go and we update these guys. And updating these guys means we're calculating the hash. This is not a simple addition like this. This is actually a Pedersen hash, which is fairly complex operations. So this easily adds up, and that is the reason why synchronization on Unstoppable and these wallets it takes hours, because every time you receive a new node, you are going to recalculate the values of these hashes, even though in some ways they are the same. Well, they're not all the same, but you could figure out some of them as being the same, right? And the current implementation in the reference wallet does not use that property. Right? It doesn't use a property basically that's the same tree, right? And okay, obviously, to be fair, this can change, right? They can obviously change the implementation, and I think they are working on that. So they make usage of the fact that it's the same tree, and that will obviously improve the performance. But at this point, that's not the case, right? And the worst thing I would say is that as you have more nodes, if you add one more node, which for example CM2 is also yours, then it's as if CM2 has its own tree, right? Granted, the tree is not a full tree, and it's only up to n, up to like here 3, right? Number of levels, values that you keep track of. But every time you add a new node to that tree, you have to go for every single one of the nodes that you have, and you have to update them, right? So I hope that now it's clear why the synchronization and the maintenance of this tree is very time consuming. And now we can see so that okay, this is the way Unstoppable and Nighthawk do it, because essentially they've wrapped the ECC reference implementation, right? So they use LibRosk Zcash that implements this logic as a black box, right? So they call it to functions like that, and then that's what LibRosk Zcash does. So as a consequence, most of the wallet out there, every wallet that is like the result of integration, and I have, for example, I'm pretty sure, 99% sure that will be the case for Cakewallet. Cakewallet will also integrate with the LibRosk Zcash, and will also have the same performance profile. Right? I don't expect them to go and then do more than that. So what's the difference with now BlazeSync, right? BlazeSync, in essence, is also using the same method. So they also use LibRosk Zcash, but they are leveraged some clever heuristics. The first heuristic is that you can see that this really time-consuming part of maintaining this tree is only related and only useful if you start spending your nodes. This does not impact the value that you have in your wallet. So your account balance is completely unrelated to this tree, right? And it's only related to detecting nullifiers and decrypting the incoming funds, right? And because it's unrelated, what they do is they actually do this in parallel. There's one thread that is doing account balance maintenance, so it does the node trial decryption, and then in a separate thread, they would do this stuff, this process. So this process is like 99% of the time. The other one is 1% of the time, something like, well, grossly exaggerated, but something like that. And of course you can say, okay, well, this therefore it's not going to change too much the end result. But in terms of perception, it makes a huge difference, because the wallet has the balance. So unless you want to spend right away, you're okay with waiting. But if you go and you want to spend, right? Let's say that you recover your seed, and then that's because you want to spend right away, right? So they're gonna have to have this data structure updated as well. There's no work around this. So the second heuristics they use is the fact that if you want to spend, for example, CM4, you don't need to have the tree updated for CM3. If you have CM2, CM3, and CM4, since they are the Libras Zcash stores them as kind of independent trees with quite a lot of overlap, but in memory are independent trees. You can maintain CM4, have it ready for spending, while you work on CM3 and CM2, right? And they do it backwards, so they have scanned the stuff forward in order to do the trial decryption, but they assume that you want to spend a node that you have received recently. So they would, if for example you had CM8, they would prepare CM8 for spending, and then they would walk backwards towards CM4, CM3, and so on, right? So this also gives you the impression that your wallet is ready for spending. But again, this you may take that as you want, right? But technically the wallet is not ready. All the nodes are not ready, but you can spend some. So in terms of user experience, it's definitely way better than having to wait for the entire sync of this tree plus the node the trial decryption, which again also is done in a single thread in Libras Zcash, which takes hours, right? So the main two big improvements that BlazeSync has is the fact that the node decryption is separated into a different thread, and also that some of the stuff like maintenance of this tree is done through in parallel. So there are more than one thread working at a time, and therefore they have much better performance, at least perceived performance, because so real performance, because multi-threading improves the resulting wall clock time. The amount of work in computing is relatively the same, because the underlying algorithm is the same. We're still going to add all this stuff together, right, one by one. But the orchestration is much more efficient, right? So that's BlazeSync. And then finally, we need to talk about WarpSync. Okay? So I don't know how long I've been talking so far, but it's probably like super long. I'm very sorry about that. But I hope that at least answers some of their questions about this whole thing. This whole why some wallets are like hundreds of times faster than others. There's some kind of trickery involved. Basically, no, it's just based on the way things are done, right? And the way this thing is done. Okay, so let's go to WarpWallet now. So the synchronization in ZWallet is different because it uses the properties that I've told you about, right? The first one is that we build this tree, and we share this tree between all the nodes. So this allows us to say that if we have a 3 here, because we combined it, we found out that this is 3 here, we don't have to recalculate it for all the other nodes, right? So we share that calculation. And that means that if we have CM3 and CM4, we don't need to calculate the value 11 for both CM3 and CM4. We know that, right? We still have to calculate once, because calculating a hash is, you don't have a choice. You have to calculate once. But you don't have to calculate it for every one of your nodes if they share some commonality, some common path, right? And they will share some common path because the root is common. So at one point they will converge to some branch. So that's number one thing. The second thing here that we can use is the fact that you don't have to add the new node one by one, right? So if we have only 6, then we understand that there's not much we can do, but to take 6, put it here, 11, and then propagate that up. But now let's say that we have more than 6. We actually, when we synchronize a whole block, right? So we synchronize a bunch of transactions, and then each transaction has a bunch of nodes. And what WarpSync does is that it actually synchronizes more than one block at a time. It would take a chunk of 100,000 blocks, right? So a large amount of blocks, and it would process them in one big chunk. So that means that you don't have only CM6, right? You also have CM7. And you potentially you also have CM8. And you have lots of them, right? So what we're going to do is we are going to combine them, and we can combine them. So we put 6 here, we combine here 7, 8, and it becomes, okay, I'll put it back to the small guys. This becomes 15. Oh, I can't see anything now. Why? Why? Agree. So this combines to 15. Okay, good. And then this combines to 26. So this updates to 26. And this updates to 36. Is it? Yeah, 36. So this process of doing this way means that we were able to sum a bunch of these guys together, right? And we are able to combine them. So the combination actually can be done in multi-threaded as well, right? Because each of these sums, 1 and 2, is independent from 3 and 4, which is independent from 5 and 6, and independent from 7 and 8. So every time if you want to go from one level here to the next one, you can actually combine half of them in different workers. So you take 3 and 7, you combine them to 10. But at the same time, if you have enough threads, enough CPU power, you can ask the processor to also calculate 11 and 15 and sum them to get 26, right? Because you know that the input of 11 of this node here is completely unrelated from the nodes that are here, right? They're only related to these nodes here, right? So we can see that the calculation of this each level is highly parallelizable, right? And there's no because there's no data dependency, right? And the second thing is that the data structure that we keep for CM3 and CM4, we can update them as we go up, right? So we know, for example, CM3 uses this guy, right? CM4 also uses this guy. So when we merge these nodes here to build this level, and then when we go up, we update the data structure tracked by CM3 to say that, okay, now you point to this guy, right? Same for CM4. Now you point to that guy. So we don't have to recalculate. We just say you are pointing to that guy. or we copy the value. But copying the value is much easier than actually recalculating the value, which is a bad copy. So we go up, and we capture all the values that we need from that level, right? For every node that we have. And then we combine, again, we're using all the threads, all the cores that we have, the CPU cores that we have. We recombine them. We get this level up. Then we go through each of these nodes and we ask them, okay, now which values you want to capture? So, and then they copy their values, and then so on and so forth. So the process is very intertwined. It intertwines calculating these hashes, these least values, and it intertwined with capturing the values that are relevant for our nodes, the nodes that we track, right? And also, this process is fairly easy to batch, right? Because the more you have, the more nodes that you have, right, the more of these you are doing in one chunk. Before, you were actually updating the value here for 6, and then you would go and then you update the 7 and 8 com, and then the values would change. You can see that on the border, values start to change because if you have 7 here, the values here will be 7, but then it becomes 15 when 8 comes, right? And then you are kind of combining things that you don't need to combine. You are combining 11 and 7 from 18, but eventually it's going to be replaced by 26. So that value is not really needed. And by batching all the stuff together, we already like the jumping to the point where most of the nodes were already filled. So you can imagine this is filled like to hundreds of them. So we are saving all the middle calculations. That's kind of why it's called WarpSync, because instead of going one step at a time, we're using the fact that the combination of the tree, it would end up having the structure that we of a binary tree of these nodes being laid out like that, and that's because the placement of the nodes is easily predictable, right? They're never going to come and then change the ones that are before. They must be appended at the end, right? So you know that where the influence of a value will come. So okay, it's just kind of hand waving because I think at this point it's just about like intuition and about how the idea of WarpSync is compared to the traditional incremental synchronization, but I think that this fairly encapsulates the main idea, right? The main idea is that you don't have to calculate the hashes for values that you're not going to use, and you can eliminate the work duplication. By calculating the hash, if you need it, you only calculate once, right? And then you have these data structures associated with the nodes that you have, copy the values from the tree. So before we had basically one tree per node, and the work was repeated on each of these each of these trees, right? So it's as if you had one tree for CM3, one tree for CM4, and the logic was very, very straightforward, because the logic, you can repeat the logic in CM3 on CM4. If it works with one node, it would work with 2 nodes, right? This is obviously has major advantages in terms of correctness and in terms of implementation simplicity. But the drawback is that you don't use any data. You don't use the data coherence, but the fact that the trees are the same for the most part. Whereas the implementation inside WarpSync uses one tree, and then a bunch of guys are basically visiting the tree and picking the values as they are being calculated. Right? So the algorithm is much harder to code because there are a lot of special cases around the edges, especially the edges between blocks, series of blocks. But I think it was worth it, because at the end, the amount of calculation is greatly reduced, and that's it. There's no like magic trick about can we predict a hash? No, absolutely no way to predict a hash. So the only thing we can do is to avoid calculating a hash we don't need, and avoid calculating the same hash twice. So that if that's one takeaway from WarpSync, that's what WarpSync does. It tries to reuse the calculation as much as possible. And I think that at this point, nothing is calculated more than once. After that, there are some optimization regarding, since the calculation of the tree is heavily involves heavily Peterson hashes. There's a custom implementation of Peterson hashes, which is slightly, very slightly faster by a few percent. But anything goes. And that's it. So in conclusion, the rest of the code has we only optimize that. We only didn't optimize anything related to actually the creation of the ZK proof. The circuit, the sapling circuit is exactly the same as we use actually Libra Zcash without any particular thing. The only thing that has been re-implemented is this stuff here, right? And the synchronization workflow. So synchronization workflow was single threaded. Now it's parallelized, and it also uses the. Well, I hope it uses better the data cache. The fact that the data is persisted. Well, we do level by level basically. Once we do level this level, we know that we don't need any of the CM anymore, and we can go to this level. And then when we are in this level, we are done with this level, we can go to this level and so on, right? So we know that we have a very simple workflow in terms of how long we need the data, what data we need at what point, and how long we need it. This allows us to use less memory than other implementations. For example, BlazeSync, because it has a logic that goes forward and backwards, needs to cache the entire blockchain, lightweight blockchain in memory as long as the synchronization is underway. Whereas we have in WarpSync, we know that this is going forward. As you are updating, for example, if you are updating CM1 to CM8, then this entire tree here is frozen, and then you can go to CM9 and so forth. Right? So the idea is that the forward progression forward allows us to know which data we still have to keep, and which data can be thrown away, and that improves the memory requirement, which are fairly low actually at this point. So it works on like 1 gig or 2 gig. And also the orchestration of this stuff is delegated to libraries that take care of they take care of managing threads and using the proper amount of threads. So we just have to define the workload, all these hashes that have to be combined, and the library would take care of controlling how many threads you need in relation to the hardware that you have. But other than that, right, well, there's small things, but it's really the bigger part is this stuff. At the end, the data that this part of the algorithm produces, right? So this little green dude, right? These green boxes they're coming out of the algorithm. They're exactly the same as the ones that you would get from Zcash, bit by bit, right? So that's also a requirement that this algorithm is nearly identical in terms of output to the one that you would get from Libra Zcash, because then we can take these bits, right, the result, and directly feed them into the the rest of the library. We can feed them to the zk proof function because it's indistinguishable as far as the rest of the library is concerned. The result is the same. It's binary compatible basically. It's just that this stuff is calculated faster, right? All right, so I think that's the as much detail as I can go to without actually looking at the code. And but I think we don't really need to look at the code because that has too many. Has a lot of corner cases again that would detract us from understanding the algorithm, at least from this level. All right, I hope that was useful and I answered all your questions about what's this warp or why ZWallet is different. And again, this is it's hard to say, okay, why don't you just take this stuff and put it into LibRaP Zcash? This stuff here is probably only like 200 lines of code, right? It's really not that big, right? But the wallet itself is thousands and thousands of lines because there are a lot of other stuff, right? I will make another video about all the other features. Obviously, the main feature that I like is the fact that it synchronizes fast. So this is first and foremost is the reason why I use ZWallet. But there are other things that participate into making ZWallet, and you can't just extract that, right? So obviously somebody can do the same, right? It's not like super rocket science. It's not nearly as complicated as the other things in Zcash, so I'm sure that this can be done. But at this point, this is where we are, and I'm quite happy with the way ZWallet does its thing. All right. Okay, that's it. Again, thanks for listening. And if you have questions, please ask me on the forum or comments or Discord, and I'll do my best to address them. All right, cheers. How do I stop this stuff?